In this module, we'll describe the pressurization system, its components, controls, modes of operation, and the principles underlying its design. We will describe the way in which pressurization is achieved through the air conditioning system. The operation of the outflow valves will be detailed, and the function of the negative relief valves will be stated. The controls and indicators for the pressure system will be described. We will see how the cabin pressurization controllers determine climb, cruise, and descent schedules. Finally, we will deal with system faults, their associated alerts, and the procedures to rectify them. Pressurization is achieved by regulating the flow of air from the air conditioning packs to the atmosphere. In flight, the engines supply bleed air which flows into the air conditioning system through a series of valves. Hot bleed air is pre-cooled by ram air heat exchangers. Air cycle machines then produce a controlled air temperature output. These are discussed in the air conditioning module. Once the air has been cooled and dehumidified, it is distributed to the pressurized sections of the aircraft. The two outflow valves control cabin pressure by modulating. Pressure increases when the valves close. It decreases when they open, allowing cabin air to escape into the atmosphere. The primary outflow valve incorporates a manual control valve, whereas the secondary one has no such valve. The two outflow valves are otherwise identical. Two cabin pressurization controllers located in the rear avionics bay automatically regulate the operation of the outflow valves. The cabin pressure selector supplies information to the cabin pressurization controllers which regulate the opening and closing of the outflow valves according to a pressurization schedule. One of the controllers regulates system operation, while the other monitors the system and acts as a standby. If the active controller fails, the other one takes over system control. In addition, control is switched from one controller to the other after each landing or power interruption. If both controllers fail, the cabin pressure system automatically switches to manual mode. In this case, an alert is presented. Two negative relief valves, located on the rear pressure bulkhead, ensure that ambient air pressure is never greater than cabin air pressure by allowing air to enter but not to escape from the cabin. These are flapper-type valves and are normally held closed by light spring pressure. The flight deck, cabin and cargo compartments together comprise the pressure cell. During normal aircraft operation, pressurization of the cell is controlled according to schedules. These will be discussed later in this module. The controls and indicators are located in the cabin pressure selector panel on the overhead panel. The panel is divided into three main sections: the automatic mode controls, the manual mode controls, and the indicators. The landing altitude selector is used to set the altitude of the destination airport. Rotating the landing altitude selector sets the landing altitude of the destination airport, and this is shown on the landing altitude indicator. Turning the selector clockwise increases the landing altitude. Turning it counterclockwise decreases it. The cabin pressurization controllers use this altitude setting to compute the cabin pressurization schedule. Turning the rate limit selector increases or decreases the maximum rate of cabin altitude change. The selector does not determine the actual rate of cabin altitude change. This is performed by the cabin pressurization controllers. When the selector is aligned with the datum, the maximum rate of cabin altitude change in climb is 500 feet per minute, and in descent is 300 feet per minute. When the selector is rotated fully clockwise, the maximum rate is 2,500 feet per minute in climb and 1,575 feet per minute in descent. Rotating the selector fully counterclockwise gives a 0 rate of climb and descent. The actual rate of cabin altitude change is indicated in feet per minute by the cabin rate of change indicator. When the needle is above the horizontal, it indicates rate of change in climb. When the needle is below the horizontal, it indicates the rate of change in descent. The cabin altitude indicator shows cabin altitude in thousands of feet. The needle is in the off position when electrical power is off. The cabin differential pressure indicator shows the difference in pressure between cabin and ambient pressure in pounds per square inch. When electrical power is off, the needle is in the off position. In normal operation, automatic mode controls pressurization. Manual control is automatically selected when both cabin pressurization controllers have failed. However, manual mode can be selected at any time by pressing the pressure control push button. The manual control lever has 3 positions. When the lever is in the up position, cabin altitude increases and differential pressure diminishes, provided that the manual rate control has also been set. In the middle position, current cabin altitude is maintained. With the lever in the down position, cabin altitude decreases and differential pressure increases, provided that the manual rate control has also been set. Rotating the manual rate control clockwise increases the rate of cabin altitude change, while rotating it counterclockwise decreases the rate. The manually selected rate is shown on the cabin rate of change indicator. The Fokker 100 has an operating ceiling of 35,000 feet. At the operating ceiling, the normal maximum differential pressure is 7.46 psi. This will give a cabin altitude of 8,000 feet as controlled by the cabin pressurization controllers. The cabin pressurization controllers control cabin altitude via the outflow valves. The schematic does not show the secondary outflow valve. The only difference between the valves is that the secondary valve cannot be directly controlled manually, but is controlled via the primary valve. Bleed air passing through a venturi valve creates negative pressure which tends to open the outflow valve. The automatic control mechanism houses a torque motor which controls the amount of negative pressure and hence the opening and closing of the outflow valve. The cabin pressurization controller controls the torque motor in the automatic control mechanism. If both cabin pressurization controllers fail, manual control is established automatically. In this mode, the pneumatic controls on the cabin pressure selector control the primary outflow valve directly. The secondary outflow valve is controlled via the primary valve. When cabin altitude reaches 13,500 plus or minus 1,500 feet, the outflow valves move towards the closed position and maintain cabin altitude at a nominal 13,500 feet. This is achieved by an aneroid capsule within the cabin altitude limiter, which alters the control pressure of the outflow valve. If the cabin pressurization controllers fail, differential pressure is automatically limited at 7.65 psi by each outflow valve. Ambient pressure, measured at the sense port, is compared with cabin pressure by the differential pressure protection mechanism, and again this alters the control pressure of the outflow valve to maintain 7.65 psi. When the cabin altitude reaches 10,000 feet, a cabin altitude warning appears on the MFDUs. This will be dealt with in the malfunction section. The 2 negative relief valves on the rear pressure bulkhead ensure that ambient pressure does not exceed cabin pressure by allowing air into the cabin. The cabin pressurization controllers ensure that cabin pressure is appropriate to the phase of flight, that the rate of change is within limits, and that the maximum differential pressure is not exceeded. The cabin pressurization controllers receive destination airport altitude from the landing altitude indicator. This is normally set before takeoff. The controllers use the destination airport altitude to establish the cabin climb schedule, the cruise schedule, and the cabin descent schedule. These schedules are influenced by maximum differential pressure, destination airport altitude, cabin rate of climb, and aircraft rate of climb. For each aircraft altitude, there is a scheduled cabin altitude. For example, an aircraft altitude of 20,000 feet in climb equates to a scheduled cabin altitude of approximately 3,200 feet. In descent, an aircraft altitude of 20,000 feet equates to a scheduled cabin altitude of 2,500 feet. In the next section on operations, we'll look at the way in which the cabin pressurization controllers establish cabin altitude in the different phases of flight. In this section, we will deal with cabin pressurization during takeoff, cruise, and landing. In addition, we will look at the manual depressurization procedure. In our first example, we will examine cabin altitude during takeoff from an airport at sea level. The destination airport is at 2,000 feet. This is the selected altitude. First, the altitude of the destination airport, which is at 2,000 feet, must be set using the landing altitude selector. Once this selected altitude has been set, the system automatically establishes the cabin altitude for all phases of flight. Please touch the landing altitude selector to set the landing altitude at 2,000 feet. With doors closed and engines running, cabin altitude descends to airport altitude minus 70 feet at sea level. When the thrust levers are moved forward, cabin altitude descends another 130 feet. This prevents passenger discomfort at liftoff. The cabin altitude then climbs at the selected rate to the selected altitude of 2,000 feet, which it maintains until the climb schedule is intercepted. It then climbs according to this climb schedule. Next, we will consider cabin altitude when the destination airport is below the departure airport. In this example, the departure airport is at 2,000 feet and the destination airport is at sea level. Please touch the landing altitude selector to set it to 0 feet. As in the first example, cabin altitude first descends to departure airport altitude minus approximately 70 feet. As the thrust levers go forward, the cabin then descends another 130 feet to minus 200 feet. After liftoff, the cabin then descends towards the selected destination airport altitude at half the selected rate. This is known as the dwell rate, and, with the rate selector on the datum, is 150 feet per minute. Then, when the cabin intercepts the climb schedule, it climbs in accordance with this. Cabin altitude increases according to the scheduled climb rate until the aircraft reaches its cruising altitude. Once the aircraft has reached its cruising altitude, the cabin altitude remains steady for 10 minutes into the cruise. After 10 minutes cruise, the cabin descends at the selected rate towards the selected destination airport altitude. Cabin altitude continues to descend towards the selected altitude until it is limited by maximum differential pressure or the selected altitude is reached. If the cabin altitude reaches the selected altitude before the maximum differential pressure is attained, then it stabilizes at this point. In this case, the differential pressure is 4 psi, and so the cabin altitude stabilizes at the selected destination airport altitude. When the selected altitude is below the point at which the maximum differential pressure is reached, cabin altitude descends until it is limited by maximum differential pressure. Cabin altitude then stabilizes at the maximum differential pressure. It will not start descending towards the selected destination airport altitude until the aircraft starts its descent. During cruise, the cabin altitude has descended towards the selected altitude of the destination airport and has stabilized at the maximum differential pressure. Once the aircraft starts its descent, the cabin altitude begins to descend according to the descent schedule. Differential pressure and cabin altitude both decrease as the aircraft descends. With the rate limit selector aligned to the datum, the cabin can descend at the maximum rate of 300 feet per minute. However, the cabin will descend at the rate determined by the pressurization controller, which is well below this maximum. When the aircraft touches down, the cabin altitude descends to destination airport altitude minus 200 feet. The cabin then climbs at the scheduled rate to destination airport altitude minus 70 feet within 1 minute. Thereafter, final depressurization takes place. In the event of a diversion to an airport with a different elevation from the selected elevation, the landing altitude selector must be reset. The landing altitude indicator is currently set for a destination airport altitude of 2,000 feet. Touch the landing altitude selector to change the landing altitude to 0 feet. The landing altitude is now set at 0 feet, and the cabin pressurization controllers will recompute the cabin pressurization schedule according to this new information. If the aircraft is not at maximum differential pressure, the cabin will descend towards the new selected airport elevation. We shall now look at manual pressurization. The procedure is stated in the Quick Reference Handbook. In the manual mode, the outflow valves are controlled pneumatically via the controls at the right-hand side of the pressurization panel. The manual mode can be selected by depressing the Press Control push button. The cabin altitude can be changed via the manual control lever. The rate of cabin altitude change is set via the manual rate control knob. Placing the manual pressure control lever to the up position will fully depressurize the cabin. The cabin will remain depressurized provided the lever remains in the up position. Let us now look at the procedure for manual pressurization. The procedure is stated in the Quick Reference Handbook. Initiate descent to 10,000 feet is the first action that is required. Please follow the procedure to switch to manual control. Manual control has been established. Now follow the procedure to manually depressurize the aircraft. Now follow the procedure and set the manual rate control as required. At this setting, the cabin is depressurized at 300 feet per minute. When the cabin altitude reaches 9,000 feet, set the manual control lever to the mid position. When the pressure differential is below 1.0 psi, the seat belt and no smoking signs should be on. The manual control lever should be up, and the manual rate control knob should be set to maximum increase. Please take caution with rapid depressurization, as it causes discomfort and possibly injury to passengers and crew. Let us now consider a rejected takeoff. As in the previous example, the cabin first descends to 70 feet below airport altitude and then to 200 feet below airport altitude when the throttles open for takeoff. When the throttles are closed, the cabin climbs over a period of 20 seconds to 70 feet below departure airport elevation. 1 minute later, the cabin depressurizes. Finally, in this section on operations, we will look at cabin pressurization when a flight is aborted. If the aircraft suffers an altitude loss of 1,000 feet within 10 minutes after takeoff, or before it reaches 6,000 feet, cabin altitude returns to departure airport altitude. In this section, we will examine a single pressurization controller fault, a double pressurization controller fault, and excessive cabin altitude. When one controller fails, the other automatically takes over. In this case, the right-hand controller has assumed control. This fault gives rise to a Level 1 alert and an alert message in the left-hand MFDU. There is no procedure for this fault. Maintenance personnel will carry out corrective action after landing. The alert relating to a fault in a single pressurization controller is inhibited in the phases of flight indicated by a red box. Next, we will consider the situation when both cabin pressurization controllers fail in climb. The failure of both controllers gives rise to a Level 2 alert. An alert message appears in the left-hand MFDU, and a corrective procedure appears in the right-hand MFDU. Manual control is automatically established, but it must first be acknowledged. Touch the pressurization control push button to acknowledge that manual control has been established. Manual control has now been acknowledged. The manual cabin pressurization control procedure is stated in the Quick Reference Handbook. The manual control lever should be moved to the up position. The manual rate control should then be set to the appropriate rate of cabin altitude change. Once the target cabin altitude is reached, the manual control lever should be set to the mid position. The aircraft is climbing towards a cruise altitude of 26,000 feet, and current cabin altitude is 1,000 feet. According to the Quick Reference Handbook, the cabin altitude should be 4,000 feet. Please follow the procedure to increase the cabin altitude. Please continue with the procedure to increase the cabin altitude. The cabin altitude has now reached the target cabin altitude of 4,000 feet as stated in the Quick Reference Handbook. Now follow the procedure to maintain current cabin altitude. With the manual control lever in the middle position, current cabin altitude is maintained. When both pressurization controllers fail in descent, the procedure is as before, except that the manual control lever must be moved to the down position, as stated in the Quick Reference Handbook. Once the cabin altitude reaches the landing altitude, the manual control lever must be set to the mid position. Before landing with pressurization in the manual mode, the cabin should be depressurized. Please touch the manual control lever to depressurize the cabin. On landing, the cabin is depressurized. Note that the indications for cabin altitude and rate of descent will now be the same as those of the aircraft. The alert relating to the failure of both cabin pressurization controllers is inhibited in the phases of flight indicated. Finally, in this section, we will consider excessive cabin altitude. At a cabin altitude above 10,000 feet, a Level 3 alert is presented with an alert message on the left-hand MFDU and a procedure on the right-hand MFDU. Excessive cabin altitude does not give rise to a fault in the phases of flight indicated. In summary, let us review the principal components of the pressurization system. The air conditioning packs pressurize the flight deck, cabin and baggage compartments. 2 outflow valves regulate the quantity of air being released to atmosphere, thus regulating cabin pressurization. 2 negative relief valves ensure that ambient pressure does not exceed cabin pressure. 2 cabin pressurization controllers control the outflow valves in automatic mode and establish the relevant pressurization schedules. The controllers compute climb, cruise and descent schedules for cabin altitude. The landing altitude selector provides the cabin pressurization controller with a reference for computing the scheduled cabin altitude and rate of cabin altitude change. Before takeoff, when the throttles are opened, cabin altitude descends to departure altitude minus 200 feet. When the climb schedule is intercepted, cabin altitude will follow this schedule. When the destination airport is below the departure airport, the cabin first descends to minus 200 feet at sea level, and on takeoff it descends further towards the destination airport altitude at half the selected rate. This rate is known as the dwell rate and is 150 feet per minute. As before, if maximum differential pressure is reached, the cabin will climb at the scheduled rate. After 10 minutes cruise, the descent schedule is armed and the cabin altitude starts descending towards destination airport altitude. It continues descending until either it reaches this altitude or the maximum differential pressure is reached. On touchdown, cabin altitude descends to destination airport altitude minus 200 feet. It climbs to airport altitude minus 70 feet in 1 minute, following which the cabin depressurizes.